Hello everyone. It is a pleasure to present my work to you. Synthesis and characterization of gold-copper nanoalloys for a SERS application at low concentrations of imidazole solution. My name is Guillermo Alama, and I'm going to show you my work. The importance of nanoalloys is due to the synergistic properties that both metals provide. The combination of gold and copper is a good way to pull down the cost of gold and ameliorate the instability of copper. In the figure 1, shows a comparison between theoretically predicted structures and experimentally obtained results in mixing two different metals. Particularly, frames AD represent an ordered alloy, the ones that are gold and copper. The frames B and E represent random alloy. The frames C and F represent core and shell. A huge advantage of gold-copper alloys comes from its ability to form a solid solution all over the composition range. So, now the importance of the imidazole stems from the fact that its core is a component present in many bioactive heterocyclic compounds that are of great interest to their various biological and clinical applications. Here in the figure number 2, we'll look like histidine, adenine, adenosine monophosphate at all these important biological molecules contains the chain of imidazole. And as an application, surface-enhanced Raman scattering can detect this molecule at a very low concentrations using gold-copper nanoalloys as SERS substrate. The objectives of this work is to obtain different gold-copper nanoalloys from a different molar radius and characterize them. In the other hand, generate a SERS system that enhances the signal at low concentrations of imidazole and find its enhancement factor. The figure number 4 shows the steps to synthesize biometallic nanoparticles. In the step number 1, hexadecylamine as a caping agent was sonicated in 4 milliliters of deionized water and formed an emulsion, as you can see. In the step number 2, the gold and copper precursors were added and mixed. In step number 3, the solution goes to temperature, and when a blue light color appears, then quickly injected the reducing agent, and in this case is the glucose. Finally, in the step number 4, it continues stirring for an additional 30 minutes to finish growing the nanoparticles, as you can see. As shown in table number 1, 11 samples of different molar radius were prepared, following the before method. Okay, in figure number 5 shows experimental details of the Raman measurement. First, we added a bed of nanoparticles and deposited. Then the analyte solution was added, that in this case was imidazole. And finally, the Raman measurement was done. The results. The first results are from the zeta potential. We are interested in those with greater stability and slightly higher proportion of gold. I remark the molar relation 3:1 because it was the one that accomplish my goals. The figure number 6 shows the absorption of the most representative samples. At 300 nanometers is the plasmon of copper oxide. At 512 nanometers is the plasmon of gold. And it is outstanding how the alloys present an absorption towards the near infrared. Figure number 7 shows the transmission electron microscopy micrographs of the representative morphologies. Frame A is the TEM image at a low magnification, shows the distribution of the particles. Frame B is a TEM image of an individual pentacle gold-copper alloy, nanocrystal corresponding to a 1-to-1 molar relation. The frame C is the same nanocrystal, but a molar relation 2-to-1. The frame D is a molar relation 3-to-1. The frame E is a TEM image at a higher magnification focused on the tip of a particle of a molar relation 3-to-1. And in the frame F, an applied mask of a select area shows the de-spacing that is of 0.22 nanometers. That corresponds to a 111 planes of the gold phase center cubic. The figure 8, it shows the CERS measurements. As I said, CERS substrates were the 3-to-1 molar relation of gold-copper bimetallic nanoparticles, and imidazole was the analyte. The frame A shows different concentrations of imidazole solutions measured on the CERS substrate. It goes from concentrations of 1 molar to 1 nanomolar. And in the frame B, we have a box plot of the enhancement factor that it was found in the factor of 10 to the 6th power. Finally, the conclusions. These branch nanoalloys are exciting platforms with potential to revolutionize a variety of applications due to the tunable far-field response and a strong near-field enhancement. The confinement of the charge separation to tips of branch nanoparticles leads to a strong enhancement factor that are localized at their tips. Similar to what has been observed in metallic plasmonic nanoparticles, the plasmon resonance of multimetallic branch nanoparticles that we are using can be tuned by changing the composition of the branch as well as the composition of the core. Finally, the incorporation of a pure plasmonic metal into a branch nanoparticle is not necessarily detrimental to the localized surface plasmon resonance response. Okay, these are my references. And thanks for watching. Continue enjoying the conference.